Alright, so this is the bell work. You guys are gonna do the bell work. Take a couple minutes and try that out. Alright, so this would be a model for this. Of course, we got the number line right here. And then we got the actual answer up in count. But again, if you had wrote this as a mixed number on a test, you're going to get it wrong. The actual answer should be something like 11 tenths. Alright, take a moment and correct your homeworks. Of course, I'm not there to take scores, so we will take scores next time. You'll want to keep track of your score, you know how many you got wrong. The next slide will show the scoring scale. You will score it, and then when I get back, we'll just take the scores, but we will not be doing any correcting. So, make sure you take some time and correct it right now. All right, sub. Now is a good time to have the students get out a piece of paper from the binders so that they can take notes. Thank you for taking my class. If anyone misbehaves, I will get you. All right. So make sure you take names down, sub, so that I can find them and take care of things when I get back. Keep in mind, you guys, that this lesson is one of the more difficult ones. People struggle a lot with these two concepts. It is crucial that you guys know how to distribute for all your remaining classes. Factoring isn't as important, but it's still very important. It will be on the test, and it is the concept that almost all seventh graders struggle with. So you will want to pay attention to those slides. Additionally, the way this lesson will work is there will be many pauses so that you guys can try things on your own. Of course, you don't have a worksheet, so you will have to work those out. And then we'll do them as a class here in a moment. We did them during the lab class. So if you're in lab, you've seen this already. If you're not in lab, it may be new. And again, if you need help, you can watch this on YouTube. All right, guys, behave and enjoy the lesson. In this problem, you will compute areas of rectangles using different expressions. Look for ways to rewrite an expression into an equivalent expression that is easier to compute. Well, let's just take a look back at this area of rectangle stuff. So let's say that we did have a rectangle like, not this one. Let's say that we had a rectangle like this right here. Well, the length is usually always the longest side, so we would say that this is the length right here. And then this is the width. So if you wanted to find the area of these, you'd take the area, which is the length, and multiply it by the width. Of course, we'll have numbers for these examples, though. So here's one. Richard lives in a neighborhood with a rectangular field. Each part below shows a way to divide the field for different kinds of sports. Then, of course, we'll find the area of these. And we discuss the area is the length times the width. And right here, we can see that we got a length, which is 120 yards. So we're going to put this up in here, 120. And the width is 50. So we're just going to multiply these two together, which would give us the area. 120 times 50. Now that we've taken the first unit test, you guys can use calculators to solve this. So 120 times 50 should be 6,000. Now this is the area, so we would label this in terms of square yardage. 6,000 square yards. So now we got this new one, number 2, which we will calculate the area of both these rectangles now because it's been split up into 2 rectangles. Alright, so we want the area of this first one, and we can see that's a 30 by a 120 up in here, and this is in yards. So if I wanted the area of this one, I would do length, which is 120, times the width, which is 30. And when I multiply these in my calculator, I should get 3,600 square yards. Well, what about the second smaller rectangle? So we're going to have an area on it, these. Again, I've got a length of 120 multiplied by the width, which was 20, and that gives us 2,400 square yards. Now notice, I've labeled these differently, one in square yardage, one in yards squared. They mean the same thing, they're just written differently, so it doesn't matter which way you write those in. Write a number sentence that shows the sum of the smaller areas is equal to the area of the entire field, which is what we found up in here. Right, well, we kind of did that already, right? We found that the area of the big one was 3,600 square feet, and then plus the other 2,400. Actually, I'll stack that for you guys. So 3,600 plus 2,400. You guys remember the area of that big field? You know, 6,000. So this one is 6,000 square yards, and these two come out to a total of 6,000 square yards as well. So we're just dividing these two fields up, this field up into two fields. We're going to divide it up even further though. So like at these, right here, now we've got four small fields. Find the area of each part. So this one, the area of this one is 30 times 80. Width times length, or length times width, doesn't matter. And that would give us 2,400 right here. And then we got at these, which is 30 by 40, which comes out to 1,200 square yards. And then at these, which is 20 times 80, which would give us 1,600. And then this final one right here, which, I don't know, 20 times 40, which is 800 square yards. That is the area of each part. You should label those, by the way. I just ran out of space. Write a number sentence that shows that the sum of the smaller areas is equal to the area of the entire field. All right, let's do that. All right, well, if we look at that, this one right here, this one was a 30 by 80 field. And then we're going to add these, which was 30 by 40 up in here. Then we'll add these, which was 20 by 80. And then this last one, which was 20 by 40. Now on the other hand, if we look at just the whole big field, so this whole side radical, that side is 30 plus 20. And then this side radical, and that's the length or the width. We're going to multiply that by the other length or width, so that would be 80 plus 40. And of course, if we added all this together, we would get 6,000 for both of them. So. All right, use what you learned in question A. Write two different expressions to find the area of each rectangle. Tell which uses fewer operations. So this one, if we look at the whole rectangle radical, we got 3 plus 7, that's the length. And then the width is this 12 radical. So multiplied by 12, length times width. And of course we'd find that area to be 120 square units. But if we split this up into two smaller rectangles, then this one is a 3 by 12. So 3 times 12. And then we will add the other rectangle, radical, which is a 7 by 12. Which also, when we calculate this one, we would get 120 square units. So this one was 7 by 12. Okay? Hopefully this is kind of looking a little familiar because this property that we're actually covering is not new. This one has 4 rectangles again. That's okay. This one's a 4 by 3, so we'll write that over here. And then in addition to that, we got this 4 by 7. Then in addition to that, we got an 8 by 3. And then in addition to that, we got an 8 by 7. Well, if we look at the whole big rectangle, we got this 3 plus 7. And then this 4 plus 8 side. And that would be length times width. That would give us the area as well, which both of these, again, is going to be 120 square units. Notice, once again, that they just took the previous rectangle and split it up. Like these two, like, for example, number 1, they just put a line right here. And they split that other side up. That's okay. Get rid of that. Alright, number 3, again, it's been split up into 4 rectangles, so this is a 3 by 17. 3 by 17. So let's write that down here. 3 by 17 plus the next rectangle, 3 by 4. And then plus this one, which is a 2 by 17. And then plus this last one, which is a 2 by 4. Well, what about the big one? Well, we got this length, which is 17 plus 4, which is the full length, times the width, which is a 3 plus 2 length. And it looks like that would be, both of these would add up to 105 square units. And again, I'm using my calculator to solve those. Some of you guys can type those both in as just exactly as you see them, and the computer or the calculator will calculate them for you. Others of you may have to simplify them a little bit and then put them into the calculator. But the calculator will do all that work for you. It's very nice. This one is the same rectangle, but now it's not split up into so many parts. For example, we got this 5 by 17 rectangle. And then we also got this 5 by 4 rectangle. And if we add these two together, we have the area of the full rectangle. But we can also consider this length, which is 17 plus 4. And if we multiply that by the width, which is 5, we would get, once again, 105 square units. So there's all four of them. Sorry, there's 120 square units. Draw a rectangle whose area can be represented by 7 by 11 plus 9. Okay, this is pretty nice. So we are going to need a rectangle faux show. This will do. It doesn't have to be proportional, by the way. So I'm going to make this one the width, which would be 7. And then the width, the length rather, I'm just going to need to split this rectangle up into two parts. So one of these parts is 11 and the other part is 9. Bam. Now I have a rectangle represented by that expression. It didn't ask us to find the area, so that's all. Alright, 2, write another expression for the area of the rectangle in part 1. Well, again, we had this rectangle, something like these. It was split up. This is 11 and 9 and 7. Well, if we wanted to, we could find the area of both rectangles. So that would be a 7 by 11 and then plus a 7 by 9 rectangles. But of course, if we wanted to find just the whole thing, I guess that's what this is showing too. So now we've got two expressions. Alright, draw a rectangle whose area can be represented by 3 plus 1 times 3 plus 4. Alright, we should have, and let's show a rectangle like these. Picture may help us. So, I've got two length and width right there. One of the length has been cut up. So let's go and cut this up right here. And then the width also has been cut up as well. So we'll slice this once again. And it may not be proportional. It doesn't have to be. So I'm going to say this is 3 and that's 1. And then this other one is 3 and 4, like these. So now it gives us a length, which is 3 plus 1, and then a width, which is 3 plus 4. But it wants another expression for the areas. So again, we just need to look at this and find the area of each one. So this one is a 3 by 3 rectangle. This one is a 3 by 4, a 1 by 3, and a 1 by 4 rectangles. So if I wanted to write the equation or expression for these, I would have 3 times 3 plus 3 times 4 plus 1 times 3 plus 1 times 4. Alright, write an expression to represent the area of the rectangle. Right, on this one, we've got, well, the length, we'll just say is 8, and the width is x, so this would be 8 times x. And hopefully you guys see now that we're using x as a letter or a variable. Why we don't use multiplications as x's as multiplications. There. Alright, write two different expressions to represent the area of each rectangle below. Okay. Well, the first one would be to, let's look at A actually. So we can find the area of each individual rectangle. So this one would be 3 times x. And this one is 3 times, I'm sorry, not 3. 2 times x, there we go. And if I combine these, I would just have a 3x plus a 2x. The other way is to find the area of the full rectangle. So that'd be 3 plus 2 times the length, which is x. But if you wanted to simplify that, you could as well. 3 plus 2 is 5 times x. So we did 3 different expressions for this one, all of which are good. Alright, for B, this one, this small rectangle is 1.5 times x. Now, we don't put the multiplication between those two all the time. So if we don't show the operation, it's just, we can assume that it's multiplication between. On the other hand, we have this other rectangle, which is 1.5 times 5. So the two expressions we have is the two small ones. 1.5 times x plus 1.5 times 5. But we could also do this where we got 1.5 and then multiply this by this length, which would be x plus 5. Find the missing parts. So given this first expressions, or just any of these, Like this one, we need to be able to figure out the missing part here. Same with these two, and then this one. Alright, and there's a couple more for us to try. Alright, let's figure these out. So this is a 12 by 6 by 4, 6 and 4 rectangle. So here I've got a 12 by 4, so the other one would have to be the 12 by 6 portion of that. I mean, if it helps, we could draw the rectangle for this thing, right? 12 and then 6 and 4. So this one is 12 times 6 plus the 12 by 4 rectangle. What about the next one? Well, we got the 2 by n, and then the other one is the 2 by 4 rectangle. Again, if it helps, you can draw these out. This one, we've got an n by 5 and an n by 5 rectangles, so if we wanted to make this one big rectangle, it would be an n times 5 plus 3. This next one, a 3 by 5, a negative 3 by 5, so this other one would also be a negative 3 by 7. And it's shown here, this is one side, negative 3, and then this is the 5 and 7 side. On this one, it's showing the multiplication, just it doesn't show it. Okay, so 4n and then 11n means we've got a 4 and 11 here. Again, it's just showing the different ways the rectangles are set up. Alright, this next part, the rectangles in problem 4.2 illustrate an important property of numbers and operations called the distributive property, which you guys should be quite familiar with. This property shows that multiplication distributes over addition. Yeah, if you guys don't remember this property, it's fine. When you think about a multiplication problem like 512 times 5, we can split this up into place values, 500 times 5 plus 12 times 5. Or 10 times 5 plus 2 times 5. Whichever way. But we're always using the distributive property here. It's very nice. Alright. You can use the distributive property to rewrite an expression so that one is easier to calculate or gives new information. You can do this in two ways. One, suppose an expression is written as the product of two factors, one of which is a sum. You can use the distributive property to multiply one factor by each number in the second factor. This is called expanding the expression. So, for example, this first one would be a rectangle that's been split up like this. The second one is, well, it's the same thing. Yeah, it's just finding the areas of each individual one. I apologize. So this one is kind of like finding the area of a big one. And it would work the same with these other twos as well. Just now we've got a variable. Suppose an expression is written as a sum and the numbers have a common factor. You can use the distributive property to rewrite the expression as the common factor multiplied by the sum. That's called factoring, and we'll get into factoring as well. Do you think the distributive property can be used to expand or factor expressions with subtraction? Explain your reasoning. Yeah, we can. All right, I'm going to use the distributive property to expand these, but I'm going to use a model to show it. For example, these, we have this rectangle right here, and it's been split up into two parts. One is 3, the other is 2, and this is a length of 5. So, we got a 5 times 3 right here, and the other one is a 5 by 2, which means this is a 5 by 3 plus a 5 by 2, and that would work as well. The other way to use distribution is to show rainbows, which is probably what more people are familiar with. So we got the 5 to the 3 and then 5 to the 2, so I'm distributing the 5 into the parentheses. So the first one is 5 times 3, the second one is 5 times negative 2, and we'll keep this operation between. And it would work the same way with the model as well. Alright, what about these two new examples? So I'm going to use the rainbows from now on, unless you guys ask for the model. So distributing the 5 in here. 5 to the 3 and then 5 to the 2. So 5 times 3 and 5 times 2 with the operation between minus. Same with this one. I got 5 times 3 first, then 5 times negative 2. It's a negative. And our operation minus between. Alright, let's go ahead and find the value of these. So, right here, this 3 and 2 becomes a 5, so that's becomes 5 times 5, which is 25. This one is 3 plus negative 2, which is 1. So that becomes 5 times 1, which is 5. Same with this one, 3 minus 2 is 1. So 5 times 1 is 5. Right here, this is going to change to a plus, so this becomes a 5 plus times 5 rather, which also is 25. Does the distributive property seem to hold for subtraction? Yes, it does, as long as we keep the operations the same and the signs the same. 'Cause we're just distributing numbers into a set of parentheses.